Hello, my little mathematicians. Today we're going to review GCF. Okay, so let's go ahead and get started. And if you remember, there's several ways that you can find the GCF. Okay, you can list all of the factors and then find the greatest one that they share, rather intensive. Okay, or you can do the factor tree method, okay, where you list any set of factors that can multiply to that number and keep going till you get down to its primes. Then list the primes in order from least to greatest. And we did the same thing for this one. And then you see which primes they share, multiply those together, and that's your GCF. Okay, or you can do what's called the upside down birthday cake, or what I like to call the ladder method. Okay, you list your two numbers, you pull out what can go in. 2 times what is 24, 12. 2 times what is 64, 32. And if they have anything else in common, you pull that out and you keep going until you end where you can't pull anything else out anymore. And then you multiply all the factors along the side. And that would be your GCF. Okay, so first off, I'm going to show you the ladder method because that's my favorite one. So if I have the two numbers of 36 and 45, okay, go ahead and write those and then draw my little ladder. I'm going to pull out what they have in common. So what can go into both 36 and 45? Well, I see that 9 can go into both. 9 times what is 36? 4. And 9 times what is 45? 5. Can I keep going? Can anything go into 4 and 5? Nope. So then that's my GCF right there along the side. 9. Done. Okay, again, that was the ladder method. And some of you were like, wait a minute, but mine look different. Okay, well, even, I don't have very much space, do I? 36 and 45. Let's say you didn't see that 9 could go in. Instead, you saw 3. Well, 3 times what is 36? 12. 3 times what is 45? 15. Can you keep going? Can anything go into 12 and 15? Yes, 3 can. Okay, so then you pull out a 3. 3 times what is 12? 4. And 3 times what is 15? 5. Can you pull out anything else? Can anything go into 4 and 5? Nope. So you multiply those numbers along the side. 3 times 3 gives you 9, which is the same answer as up above. It should be because you're doing the GCF of the same problem. I was just showing you that whether you started with 9 or 3, as long as you don't make a math error, you should still get the same answer. Okay? Let's do the ladder one more time. So right here, I want to do it of 9 and 12. Again, if you ever want to try any, pause the video, try it, and then unpause it and come back, that's fine. In fact, it's recommended. So right here, what can go into 9 and 12? 3 can. Well, 3 times what is 9? 3. And 3 times what is 12? 4. Can anything go into 3 and 4? Nope. So I'm done. That's my GCF right there in front. Okay, that was the ladder method. That's my preferred way. It makes it so nice and easy. But the official way that like kind of makes more sense and demonstrates what this is the listing factors method. Okay, and if you like this way best, fine, you can do this for all the problems. You'll just notice that most of the time I'm going to show my work the ladder method because it's easier. But if this is the way that makes most sense to you, you should still come up with the same answer as us, okay? So I have the number of 6 and 18, right? So first of all, for 6, what are all the factors of 6? Well, you have 1 times what? 1 times 6. And 2 can go in times 3. And then 3 is my next number, which is already used. So my factors of 6 are, this is what's nice about listing them in order. Once you get to a number you've already used, you know you're done and you've got them all. And they're already in order. Go down and then up. 1, 2, 3, 6. So 1, 2, 3, 6 are all the factors of 6. The other number they wanted was 18. So start at the beginning, go in order. 1 times what? 18 is 18. Can 2 go in? Yep, 9 times. Can 3 go in? 6 times. Can 4 go in? No. Can 5 go in? No. Can 6 go in? Yep, and it's already used. So now I know that I am done. So I'm going to go ahead and list all of the factors from least to greatest. So right here, go down 1, 2, 3, and then up 6, 9, 18. So 1, 2, 3, 6, 9, 18. So there's all the factors listed. And yes, they share 1, they share 2, they share 3, and they share 6. But what's the greatest number that they share? A 6. So my GCF would be 6. Okay, because it's the greatest factor that they have in common. That way is a way that makes most sense, but ew, gross. That's a lot of work, right? So much easier. It still gives you the greatest number that can go into both numbers. All right, finally, the one method that I haven't showed you yet is the factor tree method. Okay, so we have, let me write up above, factor tree. Okay, we have 24 and 64. Let's do 24 first. What do you think? What times what is 24? I mean, you could have said 2 times 12, 3 times 8, 4 times 6. All of those are correct. I'm going to start with 4 times 6. Okay, if you start with something different, as long as you keep going down to primes, we'll still end with the same ending prime factorization. Okay, is 4 prime or can I keep going? Not prime. Let's keep going. That breaks down into 2 and 2. So circle those. Those are both prime. Is 6 prime? Nope. Keep going. What times what is 6? 2 times 3. Prime, prime. All right, all done. We broke it down to primes. It's made up of 2 times 2 times 2 times 3. All right, my other number was 64. I don't know about you. I mean, yes, 2 can go in, but I see 8 times 8. Okay, and the bigger number you start with, sometimes the easier it is to break down. So what times what is 8, 2, and 4? 2 is prime. 4 breaks apart to 2 and 2. And then again, 8 breaks down into 2 and 4, prime. But 4 breaks down into 2 and 2. So you have 1, 2, 3, 4, 5, 6 twos. 1, 2, 3, 4, 5, 6 twos. And then once you have the prime factorization of both numbers, what that actually means is that all the numbers are prime because it's the prime factorization, and they're all factors. Again, prime factorization, meaning they're all numbers that can multiply to become this original number. So when you multiply all this out, you should get what you started with. 2 times 2 is 4. 4 times 2 is 8. 8 times 3 is, you guessed it, 24. If I were to multiply all this out, I would get 64 at the end. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. And 32 times 2 is 64. Okay, so if you know that you're right, if when you multiply out your prime factorization, you get the same number you started with, and all the numbers in your prime factorization are indeed prime. Okay, now to find the GCF, I want to find the ones they have in common and multiply them together. So they both share 2, and they even share another 2, and they share another 2, but there's no 3 in this list, so that's it. They share 3 2s, so 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8, which means the greatest number that can go into both 24 and 64 is 8. Hopefully you got that, no matter which method you chose to use. So these are all 3 methods: listing factors, factor tree, or ladder method. You're going to see me using pretty much the ladder method all the time because so much easier. All right, let's go ahead and get started. So we have the first one of 12 and 15 up here. All right, what can go into 12 and 15? Well, I think that 3 can. So 3 times what is 12? 4. And 3 times what is 15? 5. Can you keep going? No, nothing can go into 4 and 5. So 3 is my GCF. Okay, next one. What can go into 63 and 45? I see 9. 9 times what is 63? 7. 9 times what is 45? 5. Do those have anything in common? Nope. So that means I'm done right here. My GCF is just 9. All right. Next one says 20 and 24. what would you pull out? I see a 4, but let's say you didn't see that right away. What if you instead started with 2? 2 times what is 20? 10. 2 times what is 24? 12. Can you keep going? Yeah, because what can go into 10 and 12? 2 can. And 2 times what is 10? 5. 2 times what is 12? 6. Can anything go into 5 and 6? Nope. So go ahead and multiply those. And 2 times 2, you get 4. There you go. That's your GCF. Okay, down here, you have 28 and 52. Actually, it's not 28. That's a 26. They're both even. So I just see 2. Okay, 2 times what is 26? 13. And 2 goes into 52. How many times? I'd probably have to do some long division here. 2 goes into 5 twice. And 2 times 2 is 4. Subtract that, you get 1. Bring down your 2. 2 goes into 12. 6 times. Goes in evenly. So 2 times 26 is 52. Do you see anything that can go into 13 and 26? Yeah, 13 can go into both because 13 times 1 is 13, and 13 times what is 26? 2. Do those have anything in common other than 1? Nope. So multiply those, and you get 2 times 13, which is 26, meaning the biggest number that can go into 26 and 52 is 26. Okay, if you haven't tried any yourself, I suggest pausing the video, trying it, and then unpausing and coming back. And again, if your ladder, when you come back, if your ladder looks a little different, that's okay, as long as you still have the same ending answer. And that'll happen no matter what you start with, as long as you don't make a math error. Okay, I started with 2 because I couldn't think of anything else that went into both of these. So 2 times what is 36? 18. And 2 goes into 150 times. Okay, again, all I saw is that they're even, so I did 2. 2 times what is 18? 9. 2 times what is 50? 25. And nothing can go into 9 and 25, so multiply my GCF along the side. 2 times 2 is 4. Okay, next one. Remember, you can always speed up or pause the video or slow it down. Okay, whatever speed works best for you. What can go into 35 and 77? 7 can. 7 times what is 35? 5. And 7 times what is 77? 11. Can anything go into 5 and 11? No. So then over here, that's my GCF. It's 7. Okay, next one. We're just rocking right along here. What can go into 56 and 84? I see 7. 7 times what is 56? 8. And 7 times what is 84? 12. Again, if you start with something different, that's fine. We should still get the same answer. So if you start with something different, pause it. Keep going with your tree. Watch, we'll get the same answer. What can go into 8 and 12? 4. And 4 times what is 8? 2. And 4 times what is 12? 3. Okay, I can't go anymore, so I'm done. 7 times 4 is 28. That's my GCF. And as long as you kept going until you couldn't go anymore and didn't make any math errors, you too should have gotten 28. Okay, 56 and 84. Does something seem wrong? Yeah, because it's the same problem we just did. So let's say I didn't see 7. Maybe some of you guys started with 2. Well, 2 times what is 56? 28. Okay, and 2 times what is 84? Well, half of 8 is 4, and half of 4 is 2. I can't think of anything that could go into both, but they're both even, so I know 2 can. And 2 times what is 28? 14. And 2 times what is 42? 21. Okay, I know that 7 could go into both of those. And 7 times what is 14? 2. And 7 times what is 21? 3. I can't keep going, so I'm going to multiply these. 2 times 2 is 4. 4 times 7 is 28 again, because it's the same two numbers I was finding the GCF of. So some of you guys may have started with 4 and then gotten 7. Some of you may have gotten 2, 7, and then 2. It's okay. No matter what, when you multiply it, you still got 28. I hope you're getting the point that your ladder can look a little different. Don't freak out if yours looks a little different from your teacher. As long as you don't make a math error, you'll get the same answer. Okay, what goes into 18 and 81? 9 does. And 9 times what is 18? 2. And 9 times what is 81? 9. Can you keep going? Nope. So there's your GCF. It's 9. Okay. Let's do a word problem because you're like, what was the point of this? This is where GCF would actually come up in real life. It says volunteers are preparing identical backpacks for refugees. There are 32 maps and 24 dictionaries to use for the backpacks. What is the greatest number of backpacks they can prepare using all of the maps and dictionaries? So they will, these are expensive, right? Maps, dictionaries, they're not free. I don't want to waste any. So I don't want any of them to go to waste, but I want the greatest possible number of backpacks to be used, and have an equal amount in each one, because we want everything to be equal and fair. This is where you do a GCF problem. So you have 32 maps and 24 dictionaries. So let's find the GCF. What can go into both? 2 can, because they're even. 2 times what is 32? 16. And 2 times what is 24? 12. I see 4 can go into both. 4 times what is 16? 4. 4 times what is 12? 3. Can I keep going? Nope. So along the side, you have 2 times 4, which is 8 backpacks. Now here's the really cool thing about using the ladder method, which is why it's one of my favorites. So the GCF tells you how many backpacks you're going to use, like the number of groups of whatever it is you're talking about, right? And then these numbers down here actually stand for something. So 32 was talking about the number of maps, right? So that means there's 8 backpacks, and in each backpack, there's 4 maps. Do you think you can figure out what this 3 stands for? What was 24 talking about? 24 was talking about the number of dictionaries. So there's 3 dictionaries in each backpack. So there's 8 backpacks, each with 4 maps and 3 dictionaries. So isn't that cool? I wish they would have taught this way when I was in school. All right. Right here. Next one says a fruit salad made on a TV cooking program requires chunks of cantaloupe and honeydew. Yum. What is the greatest number of servings that you can make using all of the fruit if you have 30 chunks of cantaloupe and 42 chunks of honeydew? So I have 30 and 42. Well, what can go into both? 6 can. 6 times what is 30? 5. And 6 times what is 42? 7. Can you keep going? Nope. So there is my GCF, 6. So that means I have 6 servings that I can make. And in the servings, I'm going to have 5. 30 was talking about the amount of cantaloupe, and 7 chunks of honeydew. There you go. Okay, and again, just a reminder, 30, 42. Your tree could have looked different. You could have started with 2. 2 times what is 30? 15. 2 times what is 42? 21. And then you would have seen 3 can go into both. 3 times what is 15? 5. 3 times what is 21? 7. I can't keep going. So there's my GCF along the side. 2 times 3, which is 6. Okay, last one. If you haven't done it by yourself yet, please do this word problem by yourself. And then come back to us. Right, you're back with us because you paused it, right? And then you unpaused it. It says the florist is preparing identical flower baskets for a banquet. He has 72 tulips and 60 roses. What is the greatest number of flower baskets he can prepare using all the tulips and all the roses? Because, we don't want to throw any flowers away. They're pricey. What can go into both? I can't think of it off the top of my head, but I know that they're even, so I'm going to start with 2. I know that 2 times 36 is 72, and 2 times 30 is 60. Okay, I see 3 now. 3 can go into 36 12 times, and 3 goes into 30 10 times. And now I see 2 can go into both of those. 2 times what is 12? 6. 2 times what is 10? 5. Can't keep going, so multiply along the side. 2 times 3 is 6. 6 times 2 is 12. So you have 12 baskets. All right, if you got 100% on this warm-up, awesome job. You're off to a good track. Okay, again, if you pause the video a lot and then you tried it on your own and came back with us, remember that since there are 3 methods you can use to find the GCF, your work may look different than mine. That's okay. Even your factor tree or ladder, if you chose to do the same method, may look different than mine, as we showed over here. However, as long as you don't make a math error, we still should get the same answer. Okay, you'll notice in a lot of the worksheets, even further on, that I prefer the latter method, so you'll see that used the most often in my work. But again, don't let that deter you. If for some reason you love the listing factor method, it works for you, or you just love the factor tree and that's what you've mastered, that's fine, as long as you still end up getting the same answer. Okay? All right, my little mathematicians, you should now be a total expert at the GCF.